Okay, so good morning, everyone. Hopefully, you guys have scanned the QR code, and we will start the course in a few minutes. Okay. Okay, for today, I decided to take some time to a little bit reviewing most of the chapter 3. Okay, so a little bit review, uh, and we can continue our chapter 4. Okay. Okay, someone asking. Someone raise your hand. So is there any questions? Okay. Is there any question? No? Okay. Okay, so for maybe around uh, 20 to 25 minutes, we'll have some uh, chapter 3 review, or precisely we will have some practice. Okay. And if you check the Google Classroom, I also put some files. There are 4 image. This is actually chapter 3 review questions. You can skip some parts that is not really in our uh, lecture, like the hyperbolic and the exponential growth and decay. You can skip, and I think also the physical phenomenon, you can also skip that. So you can try to look at those files, and hopefully if you have any questions or anything to discuss, you can let me know which part you want to discuss. So this is not an assignment, not an assignment, just for your own practice. Okay. And then I'm planning to have a quiz. Okay. So I will open the quiz from weekend until several days. Okay. So you can choose which day you are preferable. Okay. So that's it for the information. Okay, let's start with some practice. Okay, I will give you maybe 1 or 2 questions related to the chapter 3. Okay, let's start with Okay, sketch parabolas. So let's try this. I will give you a few minutes to see the question and probably try to solve it. Okay, so sketch parabolas. Why I'm writing sketch parabolas y equal x squared and y equal x squared minus 2x plus 2. The question is, do you think there is a line that is a tangent to both curves? This is so obvious, right? It should be yes. And then if so, find this equation. So you need to find the equations that is a tangent to both a curve y equal x squared and y equal x squared minus 2x plus 2. So actually, sketching the parabola is maybe helping you to see where is the tangent or how the tangent will be. You can try drawing in the graphing calculator if you have, or if you want to draw smoothly to see how the tangent will be. Anyone have the answer? Can write down on the chat box for online student. Okay, maybe drawing first. Let me draw first for the parabolas. Okay, probably this is the y equal x squared. Y equal x squared. there. And if you look closely, the y equal x squared minus 2x plus 2, I can rewrite this in the form of x minus 1 squared plus 1, right? Okay. And then this is actually the same x squared. X squared moves to right and upward 1 unit. So right 1 unit, upward 1 unit. Oh, yeah, good, good. X minus 1 over 4. Yeah, correct, correct. Okay. Okay, so we can have the same identical x squared, but with different vertex, okay, or different action point. And let me make it more clear. So maybe this is 1, and this is also another 1 here. This is the new vertex, 1, 1, the new vertex. Okay. And then, oh, let me write this is y equal x squared minus 2x plus 2. Okay, then I have this tangent like that. Maybe make it more clear. Okay. So this is the tangent for both curves. Let's write y equal, let's say mx plus 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 c. Okay. Now to solve this, uh, we are going to find the slope, right? We are going to find the slope in which the parabola has the same slope, right? The same line, the same tangent at that point. So we are going to observe and maybe naming with some variables. Okay. So for example, this part here will be maybe P and then Q or AB or maybe AB, AB. Okay, because I think I too often for P and Q. Let's change to AB. And then for A, this part here, uh, let's say we are having some x. Okay, this is x equal, let's say A, okay, the small a. And for B, we have also another x that is small b, like that. So if we are observing both curves, okay, we will have each curve, okay, each curve, let me write here. So each curve A, x at x equal A, then y will equal A squared, right? So this is y equal x squared, okay? And for B, this is B, and then B squared minus 2B plus 2. At least that is our point, okay, for A, B. And then to find the slope, to find the slope m for this tangent line, we can look at this AB and then we can make out a triangle. And we know that the difference in y and the difference in x, the delta y over delta x, that is also our slope, right? So our slope here will be our m will be delta y over delta x. Okay, that is the delta y will be our b squared minus 2b plus 2 minus a squared. Okay, and divide by b minus a. Okay, that's the first equations. That's the first equation. Okay. Now the next thing is we have this general slope, right? But we also have each point have each expression of slope, which is actually the same as a and b, right? So we can write here from the uh, expression on a. So at x equal a, we can write the slope y prime is 2x, or if we write at a, this will be 2a, and this part here at x equal b, we have 2x minus 2, which is, if we evaluate at b, this will be 2b minus 2. Okay, both this both slopes essentially is equal, right? So we can also write our 2a is 2b minus 2, or a is b minus 1. Let's make this another important equation. So let's write as 2. Now, to solve the whole equations, we need to solve both 1 and 2. Okay, solve both 1 and 2. And I think it's better just to substitute the equation 2 to equation 1. Okay. Okay, so we can write m. Let's say if this is m1 here, and this is m2 for a and b. We can write m equal m1 equal m2. Okay, we can write b squared minus 2b plus 2 minus a squared divided by b minus a is equal 2a is equal to b minus 2. So we can start to solve this. Okay. So let's just start with a let me erase the last part here and just start with a, and then change a with b minus 1. So change all with b minus 1 for a. So this will be cancelled. Okay, this will be cancelled. And I can write this in terms of b minus 1 squared plus 1. I can cancel this. So I will have 2b minus 1 equal 1. Or 2b is 3, b is 3 over 2. Then a is 3 over 2 minus 1, or a is half. Now, if we evaluate with the line equations, we have y at, let's say, a and a squared. Okay, so we have y minus a squared. M will be 2a, and then this will be x minus a. So change all a with half. So y and then this is 1, so x minus half. So y is x minus half plus 1 over 4. So y is x minus 1 over 4. Okay. 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 Any questions? Okay. Okay. There's no questions. Let me give you maybe one more question. Maybe just to remind you how to do some derivatives. So if I have y equals sine tan inverse 1x, and find the first derivative. And the second question is, okay, it's two questions. Let me give you a few minutes to try. I think the first one is not too complicated, right? The first one, the sine, and then inside the bracket, you have the tangent inverse x. And then they're asking what is the first derivative. Both are asking the first derivative. Okay. Okay, I think number one is should be not too difficult, right? Yeah. Oh, it's okay, but this part needed to find the derivative. It can rule. Okay, so for the first one, uh, you can directly write this becomes cosine tangent inverse x, and then ddx of the tangent inverse. Let me write with the dark color tangent inverse x. Okay, so first, usually if you have the tangent inverse and then it's related to the derivative, uh, the answer will be in terms of x. Okay, there will be no other the inverse part will be gone. Okay? So it will be in terms of x. So how do we find or how do we confirm our answer? Okay, as I mentioned, if you want to confirm, it's best to use the triangle and let the for example, this tangent inverse, okay, let this tangent inverse of x become some maybe an angle theta. Okay, so tangent theta will be an x, right? So we'll have a theta here, x will be here. This is 1. Okay. The other part here will be x squared plus 1 square root. Okay, that is tangent theta. But this is tangent inverse is theta. So sine theta from here we can also get, if you want to look for sine theta, you will get x divided by x squared plus 1. But we will have cos theta as in our answer, right? So that will be our expression. So cos theta here will be 1 over square root of x squared plus 1. Okay, so we can exchange this. So y prime will be cos. This will be theta that we are already defined at the beginning. So this will be 1 over square root of x plus x squared plus 1. And then tangent inverse derivative, this will be 1 over x squared plus 1. Or we can combine both of this. This will be making square root of uh, so half and 1, it should be 3 over 2, right? 3 over 2. This will be x squared plus 1, 3. Yeah, I think this is okay. It's simple enough. Okay. But usually there will be an options and you need to choose which one is suitable for this equation. Okay. Okay, now The second one is a little bit similar in terms of the inverse, but we can go directly. If we want to derive all this, the y prime will be, the square root is becoming, let me write here, 1 over 2 square root of 1 minus x squared, and then multiply with the 10 root. This will be minus 2x. Okay. And let's just write that first, and then plus, this will be the chain rule. Okay. So first is the sine inverse x, and then plus x, and then multiply with the derivative of sine inverse. The derivative of sine inverse, if you don't remember, that is 1 over square root of 1 minus x squared. And how, if you don't remember the sine inverse x, you can always try to derive by yourself. Okay, so for example, you can derive as, so for example, you can let sine inverse x become y or become theta. Let's say become theta to imagine that there is an angle that you are looking for, and then the sine theta becomes x. So you can also remember, draw a triangle. This is theta x1, and this will be 1 minus x squared. Okay, and then when you derive this, derive with respect to x. Okay, so you will have an implicit differentiation. So this will be cos theta d theta over dx, and then this will be equal 1. So the one that we are looking for is d theta over dx. Okay, and then we can write this d theta over dx equal 1 over cos. Our cos from here, if you look, is cos is square root of 1 minus x squared. So 1 over cos will be 1 over square root of 1 minus x squared. It's not really long. So if you're familiar with the process, when you are forget the exact formula, you can try to redefine the formula by yourself. Sometimes you may forget sometimes, okay? But if you remember that, that's really nice. That's really nice. But sometimes you will forget this formula, like I do. I always forget the formula, so I going back to this process and then make sure that the formula is correct, and then we can go back to the question. Okay? So the right part here is just to confirm how to find the sine inverse. Okay, so you can do the same process with cos inverse, the tangent inverse also. So whenever you find, you can go back to this process, and then we can go back to our question here. So sine inverse, let me write here. Sine inverse will be divided by square root of 1 minus x squared. Okay. Now, actually, if the question is asking the derivative, the first derivative, without giving any more information, I believe until this point it's still correct, because this is after we derive, right? But if the question is giving you an options, then you need to make sure that you can simplify the form until you get a similar form with the options. Okay. So if you want to maybe simplify, you can do some algebra operations. Okay. So if you want to make some, maybe from this part, you want to make it more nice and clean form, can do that as well. This will be sine inverse x. And we can have minus x, and then we can have a nice cancellation here. We will have sine inverse x. and then another nice cancellation here, right? And the answer will be sine inverse x. Yeah, but actually, if you just stop at the beginning, that is also correct. That's also correct, unless there is another form that is given in the options. Then you need to find out that form. Okay. Okay. I think I will stop here for the review of chapter 3. The rest of the chapter 3, you can find out in the additional video I just uploaded, I think, yesterday. There are some solutions for some problems. I think six question or 5 question, I forget, but you can check it out. And every time you have the question, you can stop the video and try first, and then compare the results with my results. Okay, and that way I think that will be better. I prepare another video this week also, maybe tonight or maybe tomorrow morning I will upload. Maybe the other part will be about more about the related rates and the linear approximations. So I think, yeah, maybe 4 questions, maybe around 4 questions. And if I have another additional, I will let you know. And I think Saturday, maybe around afternoon or evening, I will open the quiz for you. So please check it out on Saturday or Sunday morning. And I will open for several days, so you can have some time to think which day you are going to perform the quiz. And remember, you can only click the quiz once, only one attempt for the quiz. So please don't forget to take the quiz. Okay. If you're missing out, then the system cannot be receive another applications, because I have set the time limit. Okay. Okay. Now we are going back to our chapter 4, and before we are going back to chapter 4, let me just go for the feedback time, some review. Uh, okay, I think you guys, for the first question, you guys get correct answer. Okay, now uh, it's fine linearizations. It's called linearization here, but if you look at the options giving you the f, okay, which means this is actually find the approximation. So if you look the approximations, you need to check approximation at a equals 0. So this is your function here, and plug in 0, you get 1. And then finding the f prime, the first derivative, plug in 0, also 1. And you can have this nice approximations that is f of x is approximately 1 plus x. And that is actually our answer here for A. Unless, okay, unless the options is in the terms of linear, like L, X, this means this should be equal. Okay, now I think the second question. The second question is more about the mean value theorem. So if you remember the mean value theorem, this is the mean value theorem here. And then looking at the X, this is A, this is also B. A is 1, B is 4, and then this will be F prime C. Okay, C is around, the minimum C is F prime C is 2. Okay, so that means, okay, from the uh, from the mathematical notations here, the F prime will determine how small the FB will be. Okay, so if you rewrite this in terms of F4, equal f1 plus the f prime 2 multiplied by 3. The smallest amount is 16. Okay, so if you change the f prime, like because f prime it can be greater or equal to, maybe it can be 3, 4, 5, 6, and it will also changing the total result, right? Okay. So how small can f4 possibly be? That is 16. We are going to the smallest f prime. Okay. 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 I think we are we are at this point here. Okay. So again, let me just review what we have learned here, especially at the big graph. Okay. So this means that at every uh, interval, okay, you can have an absolute maximum and also minimum. Okay, depend on uh, which case you have. Okay. So if you have this point here, you actually look at the x equal x0 here. Of course, if you look here, you will get the absolute maximum. Or if you want to generally say it's maximum, then that's okay. And then you check all the point, and then after that, you find out which one the highest and which one is the lowest. And that will be our absolute maximum, absolute minimum. Okay. So in maximum or minimum, the one that I think important is remember that the maximum is the change from the slope positive and change to slope negative, right? And if you have the minimum is changing from the slope negative to slope positive. And of course, at the very point, exact point at the local minimum, you will have f prime equals 0. Okay. So every time you will have f prime equals 0, that is maximum or minimum. Okay. But then we can have another point like this one here. That is actually still our local max. But we don't have f prime here. It's not differentiable, it's undefined. Okay. And at the x3, this is also slope is 0, but there is no change. So this is slope negative. This is also slope negative, right? So before negative, after still negative. But the slope is still 0. So x2 and x3 here, these two cases here are the exceptions for the critical numbers. Okay. Example of the cases. Okay. So the slope 0 or f prime 0 is not necessary to be maximum or minimum, and still we say the f prime 0 at x3 is still our critical numbers, even though it's not a maximum or minimum. Okay. Let me write the oh, sorry. Some terms that is, I believe, this is just the definitions that we already see. Okay, so absolute maximum, if you have the FC is greater to the f of x for all x in domain. So in the whole domain, then we call it's absolute. Okay, so minimum also the same. It's less than f of x for all x in the whole domain. Okay. And we can also have the local definitions. Okay. The definition is actually when x is near C. So which means you have the domain, and maybe you cut the domain into some pieces that is you can observe that is what you call a local. Like for example, this one, the big one, the highest one, we call the absolute. And if there is another one that is having a similar property, but it's not highest, we call that a local maximum or local minimum if it is a minimum. Okay. And the extreme value theorem say that if a function is continuous on a closed interval, then it has the absolute maximum value and absolute minimum value. But remember, okay, in a closed interval, you need to evaluate the endpoint. Okay, so you will have a critical number that's probably your maximum or minimum, but you are not sure it is absolute or local. You need to check the critical numbers and check the interval endpoint of interval. Which one having the highest or lowest? Okay, that's the extreme value theorem. Okay, and also from this graph here, we can have another theorem. Okay, well, let me move to the next page and then see. Okay, this the definition. Okay, so critical number. Okay, so first is if it is f prime, its f prime is 0. That's C is our critical number. Or if f prime C doesn't exist or undefined. Okay, so from what we have, let me go back first to see what does it mean. Okay, so we are saying that okay, this is a critical number. This also critical number, right? And this also critical number here. So for something that is undefined is also critical number. So here also critical number. So critical number not necessary to be maximum or minimum. Okay, so that is the definition. So a critical number of a function is a number C in the domain of functions that either f prime is 0 or f prime is not exist. Okay, then there is another also theorem. It's called the Fermat Theorem. It is actually all the theorem here, they are uh, similar, in which if you understand the previous graph, it should be fine. So Fermat's theorem it's stated that if it is having a local max or local min, the f prime exists, then the f prime of C should be zero. Okay? So it's stated that if there is a local max or local min, and that the extreme point should be f prime equals zero. Okay, so it's a forward and backwards. Okay, not necessary to be memorized. Okay. The other one, I think one more. This also, I think, pretty much similar. If f has local max or min at C, then C is a critical number of f. And then the closed interval method, this is, I think we have already doing this method. Okay. So if you want to find the absolute maximum or minimum, first is find the critical numbers, check the values of critical numbers, and then check the endpoint of interval. And then from that all that numbers, you can see which one is the highest, which one is the lowest, and that will be our absolute max and absolute min. Okay, so that is pretty much logically reasonable, right? Logically reasonable. Okay. Okay. Let me go find. I need to find the graph. Wait. Mm, okay, it's not too important. Uh, Ross theorem. Well, I think we already have mentioned that before. Not really important. I think this. Okay. Okay. So f prime is positive means the slope is positive. F is increasing, and then this is also we have discussed this before. Okay. Just making it to make sure that it's in order. Okay, so I believe the first part about the first derivative test, we already have the basics. Okay, so we can move forward. Okay, now we are going to take a look at this two graph here. Okay, now we know that from before, from the previous graph, that if you have a change in slope, okay, for example, if f prime changed from positive to negative, it will be having a local max. So you can imagine that this is going up the gradient and then going down. So you have a maximum here, right? Or you will have change from negative to positive, then you will have something that is going down here and then going up. You will have the minimum, okay? And you can also have still, like for example, negative and then still negative. So you also can have a graph like that, or positive and still positive, and you have also a graph like that. So, but if we are looking closely, okay, for example, this F and then G, we have two graphs here. If we are just looking at the first derivative or the slope, both curves is a positive slope, right? Both are having this F prime is a positive, right? And this is also G prime is a positive, right? So, but you can see the difference, right? You can see that it has different curve, right? So for F, if we take closer and then observe, at least take some points and then looking the how the tangent will be. This maybe like that, and then maybe going up, and then becoming more and more steep. Okay, so it's becoming almost vertical, right? Becoming more and more vertical. We can say this positive. Okay, so we have the positive gradient or positive m is increased. Okay, because it's from almost horizontal and it's becoming almost vertical. We can say it's becoming positive, positive, positive. Right? It's plus, 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 plus. Okay. But here, if we compare with this, if you look here, tangent may be like that, and then when you reach at B here, it's almost horizontal. In which it's almost zero, right? Almost zero. We can say this positive m or positive slope, because it's all positive, is decreased. We are not saying it's becoming negative, but it's decreased. It's not as big as when you are in A. So from A to B, the slope is decreasing. Okay, the slope is decreasing, but it's not negative. But it's not negative slope, right? Okay. Now to check this, okay, to go more deeper, we need to have another test to check. Okay. Okay. So if you want to check, we are going to have another, we call the inflection point. Okay, to understand the inflection point, let me draw the graph in the next page. Let me make it a new pages. Or maybe I will make it a little big. Let me make it here. Okay, let me make it like that. And we can have from here, okay, let's say that is the first curve, having like that. Okay. Let me move a little bit down. Okay, so from the previous graph, if we are going to have a more For example, let's say we have a graph like this, okay, the small graph. And the second one is a graph probably like this. Okay, maybe the graph from the previous one here, this one here, is taking from this graph, the whole graph. Maybe the whole graph like this. Okay, so this is F, and this is G. If you look at this having a minimum, right, and this having a maximum, so you will see that the graph with the extreme minimum, it's having, we call this is its concavity. Okay, we call this the concave upwards. So when you have like a bowl like this, we call this is the graph is concave upwards. And this part here is a concave downwards. So it's facing down this part here. Okay. Okay. So if you have change in concavity from upwards to downwards or from downwards to upwards, there will be something in the middle. Okay. For example, let me put this part down first. Okay, so if you have maybe x cube, or maybe something has the cube for the equations, maybe it will have something like this, right? Okay, so maybe this is x cube or something that has cube inside. If you look closely, and closely, you will see that this is actually facing downwards, right? It's facing downwards, or in terms of concave, its concavity is concave downwards. Okay, and after reach some point, it will have concave upwards. We say that it's concave upwards. Okay, and at certain point, okay, maybe at the very middle here, because it's just x cubed, there will be a point that is, if you remember the first derivative, we have the turning point, the critical point. In this part here, we will have, this is called the inflection point. This is called the inflection point. It's called the inflection point. So the definition is when you have concavity changes from downwards to upwards or from upwards to downwards, there will be an inflection point in the middle. Okay. Okay. Oh, I forget this. Okay, so that is the inflection point. We can say that this is changes in concavity. So you have inflection point, and if you remember, we have also the critical point, right? In the first I think last session. This is change in gradient, right? Change in gradient. Okay. Now, to deal with this concavity, we need to deal with the second derivative. Okay. So we need to deal with the second derivative. Or we can say the inflection point is when the second derivative is equal 0. Okay. Okay, so if we have this part here, this big graph, okay, big graph here, then if we want to make sure that we know how we are going to observe the concavity, we can make like this one is going downwards like that, right? At maybe until certain point, maybe here, then it will be going upwards. Maybe here is going up first, and maybe there is no change, but it's still maybe a little bit downwards and going upwards, and then downwards a little bit, and then upwards. Okay, then you can you know how to distinguish the concavity. Okay, we say the if we have f prime equals 0, this will be inflection point. And if we have the f prime is greater 0, we call this is concave upwards. Or this will be having this. Okay. If this is less than 0, then this will be concave downwards. Or it will be like this. Okay, let's compare with the graph that we are maybe familiar with and see how we can observe the concavity. Okay, let's go to the next page. Maybe any question up until here? Any questions? Yes? Mm-hmm. Concavity means the change in slope. Yeah, the slope is, so you have a curve, you have a slope, right? Okay, you have a slope. But the slope itself, it can be different in every point. So the change in slope is actually our concavity. Okay, derivative. Or if you want to maybe imagine like in physics phenomenon, you have a distance, velocity, accelerations, right? We usually, if we are having like parabola distance, like if you throw something and you have some velocity, we know that the velocity will be the first derivative of the function's position, right? And we also have acceleration in which it's the second derivative from the function position, right? It's similar to that. Yeah. And accelerations, it's not always in linear, right? The acceleration itself, it can be changed, right? It's not always constant. Okay, depends on the functions also. So if the functions may be having with the power of 4, maybe 5, and then the acceleration will be maybe power of 2, 3, right? And I think there is another terms if you derive the accelerations. I forgot the name. It's something like a. I think the name is jerk. It's the derivative, not derivative. It's the rate of change of the acceleration. Okay. Okay. Nice question. So the concavity is actually the change in slope. So if you have like this graph here, then you will have different slope. Okay. How fast the slope is changing is actually the concavity. Okay. And it will be, if we can see uh, the whole definition in terms of how the graph will looks like. So if the graph like this, then the concavity is actually going here. So it means the slope is changing from positive. Okay, slope is positive, but it's going to have a decrease at a certain point, and then it's going to be negative. Okay. Okay. Now let's see several functions that it should be the functions that is pretty much familiar with you. Okay, let's start with y equal x squared. Okay. Okay. If you look here, we have negative slope here, right? Negative slope, and then we have the slope 0, and then positive slope. And if you look at, we have a concave upwards. Of course, there will be no inflection point, right? Still upwards a whole way. And if we have the derivative, which is 2x, then we need to make a line equations, right? With the 2x. And to get into the logic of the line, we are seeing here the tangent is negative, right? The tangent is negative. So this slope is negative. So it should be start from here, from the negative part here. And this is the positive part here, right? So we are going to have, in this part here is negative, right? So the here part, this part here. So it's maybe around here, okay? And at exactly 0 is 0 here, okay? So 0, and then it's crossing 0 exactly at this point, at x equals 0, okay? So I think that's best to describe how the lines will be. Now, if we are having another derivative, the second derivative, this will be equal with 2. Okay. And now we are only having our line y equal 2. So maybe around here, that will be our line, or maybe okay, that will be our line. And of course, from here, you know that 2 is a positive, right? So which means this is positive. So that's why we have a concave upwards. Okay. So this is concave upwards. Okay. Okay, let's try another one. familiar curve. So this is x squared, derived becomes 2x, derived once more becomes 2. Okay, now the other part, let's try another one. Let's try with okay, let's try that is okay, let's just say this is our y equal x cubed. Okay. Okay. Now if we are looking at the slope, okay, we are looking at the slope, this will be the slope. Slope is positive, always positive here. And after some point, the slope becomes 0. 0 slope here. And then it's going back to become a positive slope. So before and after still positive. But if you see from the concavity approach, the concave, the concavity changes from downwards, right, to upwards. Now if we are having this, the first derivative of the x cubed, we will have 3x squared, right? 3x squared. So we are actually having or maybe this much more thinner, maybe that. If you have 1, 3, we have 2, it becomes 12. So it should be a more thinner. Yeah, maybe like that. Okay. Now this is, for example, the 3x squared. Now we are looking at, if this is y prime here, this area will be positive, right? This area is negative, right? So if we looking back here, still we have the slope is positive, 0 and positive, right? Here is actually positive, the whole thing on the left positive, and then reach 0, here is the 0, and then going back to the positive area, okay? But now it's not similar with the previous one. Now we have quadratic equations, not a linear. So we will have, if we are going to look into the change in here, we have the slope. So this is slope of slope. Okay, if you want to reuse that word. So we have another slope here. And the another slope here, this will be negative slope and this will be positive slope. Okay. If you are going to look the slope of the slope, or how to say that, if this is a complicated word. So you tend to take derivative of this and making another tangent line, or maybe a tangent to the slope. Maybe that will be better. Tangent to the slope. Tangent to the slope. Yeah, tangent to the slope. So if you have another derivative, second derivative from 3x squared, you will have 6x. And now from this tangent of slope, negative, positive, so you will have probably maybe around here, maybe like that. Okay, that's the slope. Okay. So this will be from negative to positive. Okay. And precisely at x equals 0 here, okay, at x equals 0, it is crossing the x equals 0 and changing from negative to positive. Now we are saying here that this is our inflection point that change the y prime less than 0 to y prime positive. Okay. So this line here is actually how we interpret our concavity. Okay. Concavity negative to concavity positive. Okay. Okay. Okay, so x squared, x cubed. Let's try some trigonometric, some basic trigonometric to see how we are going to draw the first derivative, the second derivative. Let's say we have the y equal sine x. Sine x, let's just focus on maybe from minus pi to pi. Okay, maybe just focus on this interval. So we can focus on here and here. Oh, maybe that's not pretty good. Okay. Yeah. Yeah. Let's say this is symmetrical and yeah. Okay. So we can first looking at the slope. We can have the slope here and having slope 0 at this point. This will be y prime equals 0. This is a negative. Okay. And then we can have a positive slope here. And let's change the color. And then somewhere here is still positive slope, and then 0 slope, and then negative slope. Okay. Now, if you are looking at the concavity, you notice that this was upwards, right? Still upwards, and then change becomes downwards here. Okay, so let's see what we are having at the first derivative. So if we have the first derivative of the sine x, the first derivative is cosine, right? So we will have a cosine. Let's say we have from let's make a line here to make sure that this is our observation area. Okay. Now it starts from this negative here, so it should be start from the part negative here and positive here. The start should be from maybe around here and maybe going there and maybe going up like that and maybe going down. It's a little bit different, so maybe I'm too big, maybe smaller like that. Okay, maybe like that. Okay, cosine. Now, if you look here, let's start to make sure. Okay, so we start from negative area, and then going back to this part here, which is the when the y prime equals 0. So this is if we continue the line, it's precisely crossing x equals 0 here. Not x equals 0, sorry. Y equals 0, sorry. Which is the y prime. Okay, so this is y prime. Y prime, this is y. And same with the other part here, y prime equals 0 here. It's changed from positive to negative, right? But again, because it's trigonometric, we can still have more derivatives to come. Let's just try one more derivative to check our conclusion. So we have tangent of slope here. The change is from here, it's going up. So it's positive, positive, positive. It's still positive, and going down, it's negative, 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 and still negative, right? But it still have another concavity changes, okay? Because it's trigonometric. It's always having concavity changes throughout all the derivatives. Okay. And now when we are having the second derivative will be the negative sine x. So if we are looking here, we are having positive here, but change in the middle. So we are going back to have another one, maybe from here. Let's make a line from here, and another line from here. So this will be this part here, and this part here. Okay. It's precisely the negative part of the original equations. So sine x, this one, the negative part will be this, right? And it's precisely true from the first derivative. It's positive, and then change in concavity. So start with the upwards and then downwards, right? So start with the upwards, and then we know that here will be our changes, right? So this will be positive and negative here. And all area here is positive area in y prime. And changes in 0 is it's here. So we are going to have crossing this area here, crossing y prime, y double prime equals 0. So this part will be the inflection point. Okay, this part is inflection point. These two parts here, because it changes the concavity, in which we can see the inflection point is out in here and here. Okay, but because this sign will always keep, you can derive more and more and more. But at least you can see how the first derivative and this inflection point we can also can figure out. Okay, now the next session, okay, for this class is aside from these familiar functions like x squared, x cubed, and the trigonometric, let's try to learn how to sketch the graph. Okay. Uh, uh, Sketch the graph from the so you will be given the graph, it's not necessarily have certain functions. So it's like a random graph. Okay, but let's try to check. Can we draw the rough sketch for the derivative or maybe the second derivative? Okay, let's try from here. Okay, let's start from there is a line there, and then there is a like that. Or maybe having from here, I think. Okay, and then this is okay. Okay, more or less, this is a curve. Okay, let's say this is f of x. Okay, and you need to make out the. Let me copy this. You need to make out the other f prime. So try in your own paper. Okay, so what will be the f prime? Okay, looks like how the f prime looks like from the this f. Okay, so probably you need to have to draw it in the paper, and yeah. So maybe in next week, because we are getting more and more focus on sketching the curve, graphing some curve from calculus perspective. I think it's best if you can join in the classroom. So and I think some of the international students already come in Taiwan and maybe still have quarantine. I hope we can meet very soon. So other students also can join next week in the classroom, because I think the necessary for the chapter is to see the graph and how we can design a graph. Okay, let me erase this part here to make it clear. If you want to make some point, that's okay. Let's say this is at -2, -1, this is 0. And let's say this is 1. And this is 2, this is 3 here. Okay, now if we break down our functions, okay, let me check the students in the class. Okay, okay. You try. Okay, okay. Okay, so if you have a line like this one, this means in the world of f prime that will be 0, right? That will be 0. So it will be maybe here, right? Up until a certain point here, and then from here you can see that it's positive. So probably it will be having a positive. So from here it's maybe going up, okay? Maybe going up. So probably, okay, probably, and because we are not sure the function is having quadratic cube or any other. This is just a random guessing. Okay, so but probably okay, we can have, if we are going to take this, so maybe here is the -2, because it's -1, this is 1. Okay, so maybe this will be like that until 2. Okay, and then we are going to see this is positive, right? Positive gradient, and then it will having a 0, and then it's having a negative gradient. Okay, so how negative it can be? We are looking at this gradient, still negative, and still negative here. But remember, we can also see the concavity. It's changed from downwards. Okay, and maybe let's say around 0 it's changed to upwards. And it's also changing the gradient here to positive. So first thing you can do is checking all the gradient and then checking the concavity. Okay, that's you can do. Now you have change in the gradient. Okay, you have change in -1 here. So at x -1, it's changed the gradient from positive to negative, right? So this will be the x -1 will be changed from positive to negative. So it's maybe it's having a graph like that at the -1. Okay. So we can maybe guessing first. Maybe this is having a curve like this. This is just a guess because we are not sure how the function will be, right? But we can still sure that it should crossing -1 because at x -1, the f prime is 0. Okay. And then because there will be a change in concavity here, right? From downwards to upwards, then we will have the slope of the tangent. Okay, so at x equals 0 here, there will be a horizontal tangent, right? As at this point here. Okay? This f double prime here is our equal 0. So it will be going down, and maybe it having a curve like that, having a horizontal tangent there, and then going up. And at this x equal 1, it still have the this having slope is 0. So which means we need to cross this, right? We need to cross this x equal 1. So we need to cross x equal 1 here. So we need to cross x equal 1. And then what is happened? So if you look at this is positive, this is negative, right? So after 1, so from 1 to 2, the slope is positive, all is positive. So it should be maybe going up like that. So it's still going up, but how long? Up until here, there's another change in concavity, right? So you will have f prime, or in this case, the derivative of f prime, the f double prime is 0. So here is f double prime 0. You will get the horizontal tangent there, this horizontal tangent. And then going back to uh, up until number 3, x equal 3. So let's say we have x equal 3, maybe here. So maybe we will stop up until x equal 3, like that. And then after that, because it's saying there's no other information, we can maybe like assuming that this will be line that is still um, f prime equals 0. So maybe this is f prime equals 0. So this will be state at 0. Okay. So this probably our guess, our sketching guess for the f prime. Okay. So for the random functions. Okay, I think I will stop until here. Any questions first? Uh, here? Yeah. Should be whole, right? Yeah, should be whole. Sorry. Yeah, correct. Should be a whole. Oh, QR code. Okay. So this should be a whole. Is there any whole again? Okay, I think just one, right? Okay. So this should be a whole here. Okay. Good. Okay, if you need the QR code, let me go back. But meanwhile, if you have any questions, please let me know. So QR code is here it is. Okay. Uh, okay, I think we can start for the feedback time for a few minutes. Okay. I hope you're ready to check. Yeah, I hope you finished the QR code. Okay, so let's start the. Okay. Okay, have you joined? Okay, we can start. Okay, anyone to want to join? Okay, anyway, let's start. Let's start. 3, 2, 1. Let's start. Okay, carefully read the questions. Okay, carefully read the questions. The graph of f prime is shown. The local max value is at x. Okay, you can choose from the options. Okay, 5, 4, 3, 2, 1. Okay. Okay. Be careful. Be careful. Okay. So 4 students got correct. I will check the answer. Okay. Good. 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 Okay. Okay. Next part. The next section. Get ready. 3, 2, 1. Okay. You need to calculate a little bit. Okay, I'll give you 2 minutes. I think enough. So you can type in the numbers. Okay, the numbers. Which X? Okay. Okay, 50 seconds. Okay, 10 seconds. Okay. 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 Good. Good. Okay. Okay. Is the student here in class? No. Okay. Okay. One more. Actually, the last part is about the survey that I need to collect from all of you. They just fill in the survey. The left is disagree, the right is agree. So you just choose which is correct with, or maybe it's suitable. So please check the survey. If you finish the survey, then you can finish the lecture, and you can leave the link, the Google Meet link. So yeah, and see you Monday. I see you on Monday. So it seems no no vacations in the weekend. We have another Monday. So see you on Monday. Oh, and if you have the schedule for other course, like the exam, if you already have the fixed schedule, let me know. Okay, then I can arrange to prepare our exam to maybe a little bit separated from others. Okay.